Mr. Tarou, in this math lesson, we're going to be taking a look at number 1 from the 2018 AP Calculus AB test. Number 1 and 2 were calculator-based questions, so we'll make sure that you know how to use your graphing calculator. At least I'll be modeling a TI-84 it's probably what you're going to be using. I'll also have a link in the description to the AP College Board website where you can download a PDF of this year and many years, the scoring guidelines, the master graders' commentaries. You can see where students missed their common errors, find the average number of points students earned on each of these 9-point questions, and so on and so on. A very good resource. People enter a line for an escalator at a rate modeled by this piecewise function r of t is equal to 44 times t over 100 cubed times 1 minus t over 300 raised to the 7th power during the time period of 0 to 300 seconds. And it's a closed interval. And then beyond that, beyond 300 seconds, we have a rate which is equal to 0. Nobody is entering the line. Where r of t is measured in people per second and t is measured in seconds. As people get on, they exit at a constant rate of 0.7 people per second. So we basically have been just given a second function, one going in, and now we have one coming out. And I don't know if I've ever seen an AP, a set of AP questions that they did not include this scenario of a rate question where there's things coming in and out at the same time. There are 20 people in line at t equals 0. So this is an initial condition which we're sure that is going to come into play. We have again the fact that we basically have another function, a description how people are getting off that escalator as well as getting on. And we have information given to us for units of measure. People per second for them getting on and off, and t is measured in seconds. Now, part A simply says, how many people enter the line for the escalator during basically that first 300 seconds? Well, remember, when you integrate a rate of change, you get an amount of change, and we are given a rate of change. We were given a function that describing the rate at which people get on, and actually another function describing, again one more time, the rate at which people are getting off of the escalator. So we just simply need to integrate the function that is describing how people are entering the line. So r of t is, and really we're concerned with this first part here, of course, so this amount is equal to the definite integral from 0 to 300 of r of t dt. And you can simply just write that for the AP test. You don't need to write in this entire part of the piecewise function that's involved with this particular question. I've been teaching calculus for about 6 years now, and I did not catch on to that. So save yourself a little bit of time, just simply write this, and we're going to make sure that you understand that with these calculator-based questions, you're probably going to be using these functions in multiple ways. So I wish I knew this in the first few years of teaching AP Calculus, but you can put this, and I strongly suggest you put this function into your y sub 1 line of your calculator, and then use that stored function the multiple times you're going to need it. Don't put in the whole expression into your calculator command just to have to enter it all over again for another question. You can literally basically put this in your calculator, replacing r of t with maybe like a y sub 1. I'll make sure if your teacher hasn't shown you that, how to do it right after this. And it is going to come out to, when you do that with your calculator, 270. And then you're going to want to interpret this number in context of this problem with that proper units of measure if you want all of these possible points. So 270 people enter the line for the escalator during, time of 0 to 300 seconds. Or you could say when t is on that interval from 0 to 300. Now let's make sure you know how to put that into your calculator and then get on to part B. I've noticed this more on the language that AP is putting onto their scoring guidelines for the more recent tests where they're becoming more rigid and more strict about your language. This is an estimate based on the model, so they basically start all of these interpretation statements, and I'm trying to get myself into the rhythm of this, and clearly I forgot. According to the model, 270 people entered the line for the escalator during the time where t is equal to or on the interval from closed interval from 0 to 300. So I have a feeling, since every scoring guideline I see starts with the model, according to the model, you might want to make sure you do that with yours, just to ensure we get that last point for our interpretation. Okay, so we're going to hit y equals, put in that function r of t, which is 44, parentheses, alpha y equals, you get the function notation up there, or the fraction notation, x over 100, come over to the side, close the parentheses, put in that exponent of 3 times, parentheses, 1 minus alpha y equals, get that fraction notation up there, x over 300, close the parentheses, to the 7th power. So we're going to second quit out of this, and we're going to ask for that integral from 0 to 300 of r of t dt. So math, go down to where it says numerical integral, lower limit of 0, upper limit of 300. Now, alpha trace will bring up that menu where you can choose where you stored the function, and we stored it in y sub 1. And we're going to integrate that with respect to the variable x. Of course, on our work it was t. And there's the 700 that we're going to write down as our answer for part A. Part B. During the time interval from t to 3, the closed interval where t goes from 0 to 300, there are always people in line for the escalator. How many people are in line at t is equal to 300? Now, we already found the total number of people that got in line. That was 270. We know that the initial condition was that there were 20 people in line at t is equal to 0, so 270 and 20 make what? 290. And we know that as people get on, so people basically aren't getting on unless they, or excuse me, yeah, people aren't really exiting unless they get on. So they're getting on for the first 300 seconds, and during that time, they're then getting off at a constant rate of 0.7 people per second. So you could actually figure out what is 0.7 times 300 and just subtract that away from the 290. But it's always a good idea to write out the calculus expression. They are looking for calculus to solve the answer. And they're going to give you some points based on the consideration of the rate at which people are leaving. So the number of people in line are going to be equal to, well, the 20 that we had in line at time 0, like when they basically opened the door or started the escalator or whatever. And then from there, you're going to add from 0 to 300 the combined rates of these people getting on, and then minus the rate at which they're getting off, the 0.7 people per second. And this is now showing the understanding of the fact you're starting with 20, that it basically is an integration of two rates of change to get an amount of change, an integration for a rate of people getting on and a rate at which they're getting off. If you feel the need to, you can write this as 20 plus the definite integral from 0 to 300 of r of t dt minus the definite integral from 0 to 300 of 0.7 dt. and then this is going to be minus 0.7x with an upper limit of 300 and a lower limit of 0. So when you plug this in, you're going to have minus 0.7 times 300. Well, we keep maybe the negative out front with parentheses. That 0.7 times 300 and then minus the 0.7 times 0. So this is going to just come out to be 20 plus the definite integral from 0 to 300 of r of t dt minus the 0.7 times 300. And you can do that math if you want. It's 20 plus what? We said earlier 270 and then minus the 0.7 times 300. And this is a calculator-based question, no problem with that. But this is a calculator-based question. You can just type this all in at one time using that saved function notation that I showed you before and just literally type in 20 plus and then go to math and calculate and then hit your integral symbol here where we go from 0 to 300. We have our function stored in y sub 1, so you'll do parentheses y sub 1 minus 0.7 close parentheses. You'll be in terms of like x, in terms of your calculator goes, and it'll bring out the correct answer of 80. So, again with that language, according to the model, there are 80 people in line at t equals 300. And that is all there is to part B. Part C coming up right now. Part C, for t is greater than 300 seconds, what is the first time t that there are no people in line for the escalator? Well, we know there's people in line for the entire first 300 seconds. So let's just start off with that. And then to that 300 seconds, we have to add the amount of time it takes for the rest of the people to, well, get off the escalator. And we just found out from part B that after 300 seconds, when you incorporate the initial 20 people that are there, the function which is describing the rate at the rate at which they get on the escalator, the function basically which describes the rate at which they get off the escalator, that there is 80 people left. Well, there's 80 people left, and those 80 people are getting off at 0.7 people per second. So we just have to divide this by 0.7 and get our final answer, which is, almost off the top of my head, 414.286 seconds. Remember, you have a calculator, and make sure you go out to 3 decimal places as you round for your AP test. You can also round to 4 decimal places, and then if you make some silly rounding error, you don't get counted against you because they only count up to the 3rd decimal place, or the tenths, hundredths, thousandths place. Part D coming up right now. Part D, last part of this question. For the closed interval from t from 0 to 300, at what time t is the number of people in line at a minimum? To the nearest whole number, find the number of people in line at this time and justify your answer. Again, this is a calculator-based question. Let's lean on that technology to help us answer this question. And it sounds actually kind of similar to one of the previous parts, where we found out how many people were in line at the minute of 300, where we had to look at the, remembering that there was basically a function describing how people got on and a function describing how people got off, but we just went straight to the 300th second. It is really the same structure, except now instead of sort of a definite integral, we need an actual function. So that's going to describe the number of people at any time that we want. So the number of people in line at some specific time is going to be equal to, well, that initial 20 that were standing there when the doors opened up or the escalator turned on or whatever. And then we're going to add a definite integral for the rate at which people come on. And I want my independent variable to be t, and I want basically an accumulation function where not at some specific point in time integrating a rate of change to get an amount of change, but just at any point in time. So that means I need to use a different variable in my integrand just to separate the variables and make it clear which one is for the integrand and which one is for, the actual variable limit of our definite integral. So we're going to say r of x dx, and then from that we're going to add in, not add in, but take away, right? Because people are exiting the escalator. And we don't really need to set up a definite integral for this because the function which is describing the rate at which the people get off the escalator is constant, not variable like the function where they're getting on. So we can just take this and subtract 0.7 times t, Now, we're asked to identify, we have a function that describes the number of people that are in line, and now we need to describe when is the number of people at a minimum. Basically, just identify maybe a relative minimum or an absolute minimum. It gives us this closed interval, and it doesn't say, where's some kind of relative minimum. What is the minimum? This is actually like an extreme value theorem problem. What's the absolute minimum that this function takes on for the closed interval from 0 to 300? And let's not forget, we're not going to be looking for sign changes of some order for a first derivative. We're looking for just where is the first derivative either equal to 0 or undefined. And this function is not going to be undefined anywhere. So we're going to find out where that first derivative is equal to 0. If this function's undefined, then the derivative wouldn't exist. We're going to be looking at where the derivative is either 0 or undefined. Sorry. And then plug those values into the function that is describing, where am I looking? The function that's describing the number of people in line for each of these endpoints and for each of the critical values for this function's derivative. So n prime of t, the derivative of 20 is 0. And now we're taking the derivative of a definite integral whose lower limit is a constant and whose upper limit is a function. So we're talking about that second fundamental theorem of calculus. The derivative of this definite integral with an upper limit of t and our integrand having those variables of x is just going to be r of t minus, and the derivative with respect to t of 0.7 t is just, 0.07. Now we have to find the critical value. We have to find out where that derivative is equal to 0 or undefined. And r of t, that's why I looked over here. This r of t being this function, this is not going to be undefined anywhere. This is not undefined anywhere, so there's not going to be any place where the first derivative is undefined. But where is it equal to 0? Well, again, we need to lean on our calculator for this. And what I like to do is we've already got this function typed in for y sub 1 in our calculator. Now for y sub 2, type in that y sub 2 is equal to negative 0.7 and find out where those graphs intersect. And when you do that on your calculator, graphing the two functions and finding where they intersect, you're going to find out that that is at the time of t sub 1 is equal to 33.013298, and t sub 2 is equal to 166.574719. And now you're going to be putting the values of 0 into this function, the value of 33.01 such and such into this function, the value of 166.574719 into, I'm pointing up here for the closed interval, but into this function, And then finally, here we go, then take that 300 and plug it into this function and get the four values which are describing the number of people, and then just look for the lowest number, round it off to the nearest whole number, and justify your answer. Well, your work there of working through that extreme value theorem and having that table of values where you're finding the four values for the number of people at 0, at 33, at 166 basically, and at 300, and just make a statement to, finalize your conclusion, and that is actually the end of the problem. So I'm going to step off, clean up the left-hand side, just write the way that you should summarize your statement and what the table looks like, and then I'll go to the calculator and make sure that you know how to efficiently type this into the calculator. Basically, don't forget that this is that reason why we want to put the r of x function or r of t function in for y sub 1 and use it as a stored function so that we don't take up all of this time typing it over and over and over again. I'm Mr. Taru. Bam! Go do your homework and get a 5 on that AP test. Okay, if you need some help with graphing, here we're at part D, trying to find where that first derivative is equal to 0. We still have that function r of t stored in for y sub 1, and in y sub 2 we're just going to put in that function y is equal to negative 0.7, and let's see what this looks like. I'm sure it's going to be off the screen, but zoom standard. Of course we're not going to see anything because our time period went from 0 to 300, so we're going to hit window when this is done. Window. We're going to make the x min 0 and the x max 300. And we are looking for where that graph is intersecting the function y is equal to negative 0.7. So I think we're probably good with the y min and y max. We're not. If we minus a negative value, we are going to get basically like an addition. So I need to take that negative out there. My apologies. So here we have the function describing the rate at which people get on the ride. We have the red line, which is the rate at which people are getting off the line, since that was the derivative that we basically got for the derivative of the number of people in line. So we're going to find out where these intersection points are. So second, calculate. We're going to find the intersection between these two graphs. First curve, yes. Second curve, yes. And we're going to just simply need to get somewhat close to one of the two intersection points. Hit enter. And there was our first value that I put on the table of, or in our work, of 33.013298. And for the second intersection point, just repeat the process. Second calc, intersect, first curve, yes, there's only two curves. Second curve, yes. Get over near the other side, and we're going to find that 166.574719 seconds. Now, I showed you the table, and we knew that there was 0 people in the line at t equals 0 and 80 people in line after 300 seconds. But what about the number of people in line at 33 seconds? Well, we had that function, which was the number of people in line. So we're going to do the original 20 in line plus math, numerical integral, so 9. We're going to go from 0 to that first time period, again, of 33.013298 seconds. And that function describing the rate at which people were getting in line was r of t, which we stored in y sub 1. So alpha trace, y1, we're integrating that with respect to x. And then that is being subtracted by the rate, or adding the negative rate at which people are getting on. So subtract 0. I keep saying that wrong, 0.7 times 33.013298. As long as I typed it in correctly. I forgot to hit the multiplication symbol. Second insert. Here we have the 3.0 or 3.803 ... people that we have in line at that particular time period. And then to change this to the second time period, you can just hit second entry, pull that up, and change these time periods, which honestly maybe that would have been easier just to type it all over again, but 158 point, okay, I'm looking at the wrong number in my notes again, 166.574719, changing the time period up here for the definite integral, 166.574719. And there we have the 158.070 people waiting in line for the escalator. And that is how you can efficiently use your calculator to help you answer this question. One more time, I'm Mr. Tarrou. Go do your homework.